Evening, everybody. I'm Derrick Pitts, Chief Astronomer at the Franklin Institute Science Museum, and you're listening to NASA's version of Clair de Lune by Claude Debussy. You're probably really familiar with the music. It's been heard so many times. But what's really cool about this is how the music has been laid over top of NASA's Lunar Reconnaissance Orbiter images of the moon. Very high resolution images stitched together in this beautiful video, and it just makes you sit and take a moment to take in all the beautiful features of it. So let's listen for a little bit. If you're just joining us, my name is Derrick Pitts, Chief Astronomer at the Franklin Institute Science Museum, and welcome to our Night Skies program for June 2024. Right now, you're listening to Claude Debussy's Clair de Lune, overlaid on top of images from NASA's Lunar Reconnaissance Orbiter satellite. This is a spacecraft that's in orbit around the moon, has actually been in service for, I think, a decade now. And it has been taking the highest resolution images of the surface of the moon we've ever seen. So I thought I'd start the program this evening with this really gorgeous piece and give us a chance to drink in some of the gorgeous images of the moon. We'll be getting started with the program in just a minute. Well, how about that, folks? That was Claude Debussy's Clair de Lune, playing over images of our moon taken by NASA's Lunar Reconnaissance Orbiter. I thought it'd be a great way to start the program this evening. After all, the moon is one of the great objects we can see in the evening skies. My name is Derrick Pitts, Chief Astronomer at the Franklin Institute Science Museum, and I want to welcome you to the June 2024 edition of Night Skies. Glad you could be with us this evening. This evening, what we're going to do is we're going to get you set up for observing all through the summer. We'll give you the information you need to know about planetary viewing, what constellations are available, and specifically, we're going to point to an astronomical phenomena that's coming up in just 2 days. Today is June 18th. June 20th is the special day. It's the summer solstice, what we call the first day of summer. I always think to understand how it is that we have seasons here on Earth. And as it turns out, other planets in the solar system have seasons too. Maybe you didn't realize that, but they do. There are a few planets that don't have any seasons. Well, let's just say they have weak seasons, and we'll talk about the reasons why. But it'll be another way for us to understand similarities and differences between our planet and the other planets of our solar system. So we'll cover those topics during our program this evening, and we'll also make sure that you're all caught up on sunrises and sunsets and things like that. So let's get started with our program. Thanks a lot for joining us this evening. Again, I'm Derrick Pitts, Chief Astronomer and Planetarium Director at the Franklin Institute Science Museum. Glad you could be with us tonight. If you're in the northeastern portion of the United States, I actually should say if you're anywhere from the Mississippi River east and north, you know it's very hot. It's going to be hot over the next few days. But this is summer, so that's to be expected. Interestingly, these warm temperatures can also be very advantageous to us for observing the night sky, because the temperature can be warm from the surface all the way up through the sky. That means we can have much better stability in our viewing of objects in the night sky. So, as hot as it may be, sweltery even, this might be a good time for you to pull out a telescope and set it up so that you can begin to learn the summer sky. Plenty of great things to see in the summer sky, and this is a good time to do it. Temperature's good. In fact, some people really like it like this, and you can enjoy the evening sky. All right, let's get rolling with some of our content. We talked a bit about what the programs are going to be this evening. Oh, the other little piece I forgot to add about content tonight is we'll talk a little bit about solar eclipses, the next ones that are coming up. I know almost everyone had an opportunity to see either the April 8th solar eclipse or the October 14th solar eclipse last year. So over the last 6-8 months, we've had this great opportunity for to catch a view of a solar eclipse somewhere around the country, and hopefully you had a good view where you were. But if you're curious about the next ones coming up, you need to know where you're going to be planning to go, because there isn't going to be another one in the United States for quite some time. So you're going to have to travel for that, and that in and of itself is an adventure as well. So if you need more time in the shadow of the moon, I'm going to help you out with what dates are coming up for the next solar eclipses. Okay, let's get rolling with where we are right now. Again, this is June 18th, 2024. We're 2 days away from the summer solstice. That means we're right at that portion of the year when we have the greatest number of hours of daylight during the course of the year. So for those of us at 40 degrees north latitude, anywhere around the planet at 40 degrees north latitude, you're experiencing 15 hours and 42 seconds of sunlight today. 15 hours, 42 seconds. I should say that's the longest that we're going to experience, and that's coming up, just let me see, 1542 on June 20th, actually, on the day of the solstice. That will be the length of time we have daylight. The sunrise is starting pretty early, 5:31 a.m., and sunset is at 8:33 p.m. So there's your 15 hours. I think this is a really great time of year to really notice how the Earth's position in its orbit around the sun affects how much daylight we actually have. And we'll talk about that in a moment. So there's our sunsets and sunrises right now. 5:31 a.m. is our earliest sunrise. That's where we are right now. We'll be there for another, 6 or 7 days. And then next week is when we'll come to the latest sunsets. 8:33 p.m. are those sunsets here at 40 degrees north latitude. Here's a curious piece of information, or a very interesting piece of information. The farther north you go, the longer those hours are. So sunset will be even later in the evening as you go further north. Guess what happens at this time of year if you're right at the North Pole? When do you think sunrise and sunset are inside the Arctic Circle? Think about that for a minute. Likewise, I'll give you the other half of that challenging question. What do you think that seasonal change in the number of hours of sunlight actually is when you're close to the equator. Think about that. Drop an answer over in our chat. Let us know what you think about that. Glad you could be with us tonight. Hello, Mike. How are you? Glad to hear you're with us tonight. Thanks a lot for joining us. And I have my Lilu Dallas multipass sitting right over there on the other side of the room. Thanks again for that. That was really a great gift. Really do appreciate it. And yes, I do have some information about the supernova that's supposed to be visible to the naked eye. We'll talk about that a little bit later. Anybody else that's with us tonight, if you have any questions, you can drop your questions right here in the chat over here on the side box of this. So please let us know what questions you might have. Okay, great. So let's talk about seasons. I really do enjoy seasons. I like the idea of how it all works with the solar system, with the Earth's motion around the sun. And so let's talk about how this works out. Here on Earth, we have 4 seasons: spring, summer, fall, and winter. And they are about an equal number of days, about 3 months for each one of those. 3 times 4 together gives us the 12 months of the year. And so we can see how they're evenly divided up. But how is it that we have seasons anyway? Is it because of our distance from the sun? No, it actually isn't, but that's a piece of it. What really causes us to have seasons is the axial tilt of the Earth. The axial tilt of the Earth. Here's what I mean by that. The Earth's rotational axis, that line around which the Earth rotates, is what helps to define our seasons. If that axial tilt is very slight from vertical, we have what are called weak seasons. Weak seasons. And there are some planets of the solar system that have weak seasons because their axial tilt is not very large. Earth, on the other hand, has an axial tilt of 23.5 degrees. And that 23.5 degree tilt away from vertical allows us to have seasons because that then affects how sunlight falls on different portions of the planet and either heats or allows the planet to cool because of the amount of solar gain that occurs on different parts of the planet. Now, the other factor that goes into this is how long it takes us to orbit the sun. What's our orbital period? Well, the 1-year orbital period for us, 365.2625 days, really locks in the length of time we have these seasonal periods, 3 months for us. But as we move further out into the solar system, guess what happens? Well, the orbital period around the sun gets longer for planets farther and farther out. As that happens, that means the seasons get longer. So we're going to take a look at a couple of other planets just to see what that's like. But first of all, let's do this. What I'd like to do is I'd like to just give you a little bit of a graphic that allows you to see what that axial tilt is that I'm talking about. And I'm going to actually use the planet Mars for this. And the reason why I'm going to use Mars is because Mars has seasons like Earth does. Our axial tilt and Mars's axial tilt are very close. They're almost the same. So I'm going to share my screen here. I'm going to go to the screen I like, and we're going to jump right over to this visual. Now, hopefully everyone can see this. This is a slide that looks like it's a black background with the planet Mars shown in different positions orbiting the sun, and there's some descriptive text around the slide. Hopefully everybody's seeing that. A couple of things I need to point out. First of all, Mars is not bigger than the sun. In case you didn't pick that up, Mars is not bigger than the sun. This is just how the artist depicted this so that the pertinent information could be more easily drawn out. Also, there are no words in space. I know you picked that up. I know you got that. But here's what I'd like you to see. The axial tilt. Here, it's referred to as rotational axis. So you'll see if you look over on the right-hand side of the screen where we have the planet Mars that has a polar cap on the bottom and it says northern summer, southern winter. That one right over there, look right at the top of the planet and you'll see there's an angle measurement of 24.9 degrees. Well, Mars is tipped away from vertical 24.9 degrees. And that means that Mars has seasons. But guess what? Here's the catch about the seasons on Mars. They're twice as long as the seasons on Earth. Yes, that's right. Each season is 6 months long. Well, wait a minute, let's put that together. If each season is 6 months long and there are 4 seasons on Mars, spring, summer, autumn, and winter, well, 6 times 4 is 24. That's 24 months. Oh, that means it takes Mars 2 years to go through its entire cycle of seasons. Yep, that's right. It takes Mars 2 years to go through an entire cycle of seasons. Well, guess what? That comes pretty close to the orbital period of Mars around the sun, just about 2 years. So now we can see that things are syncing up and matching up pretty well. If we compare this to Earth, that number at the top of the planet wouldn't be 24.9, but it would be 23.5. 23.5 degrees of tilt away from the rotational axis. We have 4 seasons, but we're closer to the sun. It only takes us 365 days to orbit the sun once, so that means that our seasons are only 3 months long. 3 months times 4 seasons, 12 months, 1 year. You can see how this all goes together. So let's think about some extremes now of this, because while this makes sense and it seems to fit really nicely, what happens if we sort of make things a little bit more extreme? So for example, let's think about the planet Mercury. We know that Mercury looks very much like the moon does, a grayish cratered surface of a planet that's closer to the sun, but Mercury has only a 2-degree axial tilt, only 2 degrees. So that means that it has very weak seasons. In fact, you wouldn't even say that it has seasons at all. They are so weak. And the same is true for Venus. Venus has a 3-degree axial tilt, so it also has weak seasons. Well, if we look at the environments of these two planets, they also have complications in terms of atmosphere. So Mercury has virtually no atmosphere at all. Venus has a very heavy, very thick atmosphere that's causing a different environmental effect to happen. So it doesn't really matter about the axial tilt in that case, being only 3 degrees for weak seasons, because the entire planet is enveloped in a cloud cover that makes the temperature underneath the cloud cover and down to the surface about 800 degrees Fahrenheit all year long. So that doesn't matter at all. We know about Earth, we know about Mars. What about the big planets of the solar system like Jupiter? Well, Jupiter has a 3-degree axial tilt, so there are weak seasons there, not very much. But Saturn has a 27-degree axial tilt, so it does have seasons. But the environment there is different, so you can't expect that it has seasons like we do, where we have spring, where all the flowers are blooming, summer, when it's hot and time to go to the beach, fall, when the trees are changing color, and winter, when it snows. That's not happening there. The environment there is always so cold that the environment stays the same. But here's how you tell the difference in seasons at Saturn. You can actually see a change in the orientation of Saturn's rings. As we orbit around the sun, and Saturn orbits around the sun, much slower than we do, but as we orbit around the sun, our viewing angle changes from season to season for Saturn, and we can see how the ring tilt changes. So let's take a look at this image right behind me here. So there's a really gorgeous image of Saturn. This is from the Fels Planetarium, and this image is a CGI image, but it works very well to show you a condition of the rings of Saturn called fully open. Fully open means that the tilt of the planet during its year as it orbits the sun is such that we can look down and see the rings fully. We're looking down onto the rings, or we could be looking up at the rings, depending upon what part of the year it is for Saturn, but you can see all of the ring. In those interim periods, at the spring and the autumn of the Saturnian year, guess what happens? The orientation changes. So instead of the rings being fully open, they then become what are called fully closed, and you can only see the very edge of the rings. So in this case, it would be as if you're looking right along the edge of the rings, and all you can see is a thin line that goes across. So that's how you can tell seasons at Saturn. How about the planets further out? How about Uranus? Here's where things get really wild. Uranus has a 98-degree tilt. Well, that means that instead of being like this, it's tipped over like this. So, guess what? In its orbit around the sun, it sort of rolls around the sun on its side. And that gives some really weird setups for seasons there. There are 4 seasons, you could count them, but guess what? Because of the orbital period of the planet, each season is 21 years long. 21 years long. So, for example, for us right now, where we have 15 hours of daylight every day at this time of year, imagine having 21 years of daylight. Well, you might think that's a great thing, but what about the other half of the year? The other half of the year, you have 21 years of darkness. So I don't think that would work for us. It wouldn't work for humans and the kind of life forms we have on this planet. But that's Uranus. Neptune is similar, 28-degree tilt, but it has a very long year because of the orbital period around the sun. That means the seasons are 40 years long, twice what they are at Uranus. And as far as Pluto is concerned, these are now super long seasonal periods because it takes Pluto 248 years to orbit the sun once. And it also has a 120-degree axial tilt. So it's really flipped over. So when you put these factors together, that's what determines whether or not a planet has seasons. So seasons as we know them here in this solar system really apply only to Earth and apply to Mars. The others are kind of extreme, either no axial tilt or a whole lot of axial tilt, and very different environmental conditions for those locations. So that's how we have seasons. So here we are right now at this time of year. Here's the other thing that these seasons do for us. If we take a look at the path of the sun across the sky during these, during the seasons, we could sort of get an idea of how that differs from one part of the year to another part of the year. Let's take a look at another diagram. I'm going to share my screen again. Let's come back. Just a second. Let me see if I can locate. Is that the one? Oh, here we are. There we are. Let's take a look at this image. So here's a drawing that is looking at a view of the sky, looking directly south. As you look at this drawing, you'll see the E for east on the lower left. You'll see the W for west on the lower right. And then you see these dashed lines or arcs marked as summer solstice, equinoxes, and winter solstice. Well, as the legend says, solstice, when the sun reaches its most northern or southern arc in the sky each year. So right now, we're approaching the upper arc. This is the path of the sun as it appears in the sky on that specific day. So on Thursday, if you were to plot the path of the sun across the sky, this is what you'd get. At noon on that day, the sun will reach its highest point in our sky at noon. We're going to compare that highest point in the sky at noon to the other seasonal markers of the year. So for example, let's go to the equinoxes. That's the next arc down. You'll see it says spring and autumn, and it says equal day and night over on the right. Well, now this is the halfway point for the sun. These are the times of the year when we have equal hours of daylight and darkness. Remember, summer solstice is when we have the 15 hours. Let's go to the winter solstice right at the bottom. It's described as the least day. This is when we have the fewest number of hours of daylight during the day, about 8 hours. Now, how does this turn out this way? Well, the way it turns out is that difference in the tilt of the angle, tilt of the Earth's rotational axis. Let's go back to that Mars image if we can. I'm going to try something here and see if it works. Hopefully you see what happened. I just jumped back to the Mars image, and we'll take the two extremes. There's on the very far right, it says northern summer, southern winter. And this is on the side of the sun that's farthest from the sun. We're going to go all the way across to the other side now where it's northern winter and southern summer. That axial tilt will determine how much of the planet is being illuminated by the sun. So for us in the summer, the top of the Earth, where we live here in the Northern Hemisphere, actually is tilted the greatest degree toward the sun. The axial tilt has the top of the Earth pointed toward the sun, so the sun appears highest in the sky. In the winter, as the axial tilt changes as the planet orbits the sun, then what happens is we have the sun at the lowest portion of the sky. And that's what you see when we look at these different lines and arcs in the sky, is we're seeing where the sun will appear in the sky on these days. Now, I have a really cool picture that also helps to depict this, and you may have seen this somewhere else too. I'm going to jump right over to here. Let me see if I can do it here. There we go. Look at that interesting figure. You've seen this figure before. First of all, this is a photograph taken of the sun every 6 or 7 days throughout the course of a year. So each one of the white dots you see is actually a filtered image of the sun, a filtered image of the sun. What I want you to pay attention to is the figure 8 pattern. This figure 8 pattern you may have seen on a globe of the world. If you haven't seen one of these, find a globe of the world someplace, and if you go and look out in the Pacific Ocean, you'll find this diagram out in the Pacific Ocean. It doesn't exist in the Pacific Ocean for real. That's just where they put it on the globe so they can locate it someplace where there isn't anything else happening. Well, this figure is called an analemma. Analemma. And an analemma depicts the sun's position in the sky every day or every so many days during the course of a year at a specific time of day. So the photographer here, Mr. Casado or Miss Casado, took a photograph of the sun at a specific time every day. At a specific time of day every 6 or 7 days during the course of the year. And this is the image that came from that. So now what you'll see here is on the top left, the sun that's the highest one up, that's on the day of the summer solstice. If you go down to the lower right, the lowest sun is the sun on the day of the winter solstice. And the one where the two lobes of the figure 8 cross, that one sun right there in the middle, that's the sun on the equinox days. And so that's what this photograph depicts. All of those things put together. And these are all part and parcel of our seasonal experience with the Earth orbiting the sun. Last piece of this is, what time does this actually occur? Well, this year it happens at 4:51 p.m. I think of it as an instant. So at 4:51 in the afternoon on Thursday, the Earth arrives at a point in its orbit where the top of the Earth has its greatest tilt toward the sun. And from that point on, those dynamics are going to begin to change. So for example, next week, we'll start seeing sunrises coming later in the morning. And then another 2 weeks from now, we'll start to see sunsets coming earlier in the evening. This really highlights the fact that you should get outside and enjoy the evenings, these long evenings now, because in a month, it's going to be really noticeable that sunset is coming considerably earlier. So next time you're outside, on Thursday, you're thinking about the seasonal change coming to the solstice. These are all the factors that put it together to make this happen on planet Earth. So think about it the next time you're out. There's one last little piece to that, and that little piece is called aphelion. Aphelion is a word that means Earth at its greatest distance from the sun. Earth at its greatest distance from the sun. Guess when that happens this year? July 5th at 1:07 a.m., our planet will be at its greatest distance from the sun. That distance is 94,510,350 miles away from the sun. You can compare that to our closest approach to the sun that happens in January, when we're some 91 million miles away from Earth. See if you can figure out how it is that the two don't seem to match up with what our seasons are like during the course of the year. Here we are at our greatest distance from the sun. Why is it so much warmer now for us if the Earth is at its greatest distance Likewise, in January, why is it so much cooler if we're so much closer to the sun? Think about it. See if you can figure it out. Okay, so much for the sun, the solstice, the equinoxes, right, seasons at other planets. Sorry about that. And aphelion as well. All things to think about as part of the dynamics of the Earth orbiting the sun. Okay, great. So I see Elizabeth has a question. Elizabeth says, is it possible for the Earth's axial tilt to change its angle? And if so, how would such a change potentially affect us? Well, the good thing, actually, Elizabeth, is that the axial tilt won't change. It'll stay pretty much the same as it is right now, 23.5 degrees. This is something that is derived from the, I would say, the early history of the Earth that gave us this axial tilt. And so that's where we are. We're stuck with that axial tilt. Changes that would take place over hundreds of millions of years. And in fact, I'm going to say it's virtually minimal, that we won't see any change in that time. However, if it could change, if the axial tilt were to come down to a minimum, well, then we'd end up with very weak seasons. If the axial tilt of the Earth became extreme in the other direction, very much higher, then we'd have seasons lasting a really long time. So that leads me to one other thing, Elizabeth, that I really need to clear up. The axial tilt of the Earth, 23.5 degrees. Okay, everybody, here it goes. Make sure you understand this. The axial tilt of the Earth as it orbits the sun does not flop back and forth like this. That does not happen. What happens is the Earth with its tilt orbits the sun like so. It orbits the sun going around in a circle with the axial tilt. That means that at some portion of the year, the top of the Earth is closer to the sun, if the sun were right here. And then at the other side of the year, the top of the Earth is farther away from the sun. And then for the solstices and the equinoxes, the Earth is right in the middle. So that's what would happen, Elizabeth. That's a great question, though. Thank you very much. Let me give a shout out to Versia. Hi, Versia. Thanks for joining us. Glad you could be with us tonight. Please say hello to your sister Donna for me. Tell her I said, hey, great to have you aboard. Thanks for joining us, folks. If you have other questions, please send your burning questions in. We'll try to get them answered for you here. All right, so now that we've talked about the sun, let's go out to the night sky and do that instead. Now, as I said before, this is a great time of year to be outside looking at the night sky, and we're going to do that right now. We're going to actually move to a star map that allows us to see what the night sky would look like at this time of this year. So here's what I'm going to do. I'm going to share my screen again, and I'm going to go to one of my favorite star map pages called Stellarium. Stellarium. I really like Stellarium. It works out really, really well for us. Let me just get my timing set up here to be appropriate for us. Here we are on the 18th, and we're going to go outside at about 9 p.m., and I'm going to share my screen for this right now, coming up here. Okay, there we are. Hopefully this has come through for everyone. We're now in what's essentially a planetarium. It's a digital planetarium. It's an online planetarium. And this wonderful app allows us to see what's going to be available in the night sky. We can begin to learn the star patterns before we even go outside. So let me just explain the parts and pieces really quickly. You can see where the star field is right in front of you. You can see where the horizon is curved around the bottom of the screen to simulate it being curved out around you when you're outside. Over in the lower left-hand corner, you'll see that it says near Philadelphia. That's the locator. And of course, you can change locations to be anywhere on the planet. And then over on the far right, the box that you see is the time and date box. And you can adjust the time and date to whatever time and date you like using the arrows that you see above and below the numbers. You can also hit a pause button that will freeze time at any particular time you choose. Otherwise, the clock will run in real time and you'll see how the sky evolves over real time. So we're out on the night of June 18th at 21:39, 9:30 in the evening we're looking at right now. And the other parts and pieces you'll see here are the red letters around the horizon that indicate direction of observing. Right now I have the sky set up to look toward the east. What I always prefer to do is start out with the sky set up such that we're looking toward the south. And of course you can see all I do is just click and drag to move this. And of course, I can always adjust it so it looks more like this if we'd like. So you're actually looking out across the horizon. I do it like this so that I dip the bowl so that we can be looking higher in the sky. Last but not least, bottom of the screen, you'll find some of the icons that allow us to add various components or elements to the sky so that we can find our way around a little bit easier. So since we're out in the summer and it's only 9:30, I'm going to advance us just a little bit here. There we go. I've advanced us. We have much darker skies. Now we have brighter stars, I should say, more bright stars in the evening sky. And you'll also notice that these green things that are here, these are satellites, by the way, just so you know. So now you can see there are stars, bright stars, dim stars. You can see where the moon is there. We'll get rid of the clock in the corner. We don't need that right now. And of the stars that you see, it might be a little bit confusing to understand what's where. So here's what we're going to do. We're going to use this icon called constellations to actually put the constellation shapes up for us. Now we can see where everything is. So we're just about we're heading into the heart of the summer sky. And heading into the heart of the summer sky allows us to see a constellation of the spring sky over on the right called Leo. Leo is the brightest constellation of the spring. And we can come all the way across through Arcturus, a bright orange star. This is actually a red giant star. We can come through Corona Borealis. We'll talk about Corona Borealis in a little bit more detail in a minute or so. And we can come through the constellation Hercules, across through Lyra, past the bright star Vega, up to the constellation Cygnus, way up here in the top left corner. Now, I point these constellations out across here because you can go from Leo right through across the top of the sky to Cygnus. So that's one way you could do it. But you could also actually, let's see, follow through in another way. Here's the other way you could follow through. You could follow through with constellations that are part of the zodiac group of constellations. You know, those that are connected to horoscopes and astrology and things of that sort. Well, here's how we do that. Here's Leo. We come down a little bit further toward the center. We can see where Virgo is. If you continue along that line, you'll come to where the moon is in the constellation Libra. And moving still to the left, we come to Scorpius. And a little bit further to the left, way down on the horizon at this time, which is just 10:15, we find the constellation Sagittarius. So we can actually follow that line through the sky if we wish as well. If we go back up to the upper left corner, these two constellations, Lyra and Cygnus in the upper left, are three of the brightest constellations of the summer sky. They actually match with one other constellation that's right down here, a little bit lower, called Aquila. Aquila. So we have Aquila, Lyra, and Cygnus. These three constellations have the three brightest stars in the summer sky: Vega, Altair, and we can just not see it up above the tab here, right in the corner, right up at the tab. I don't know if I can make that full screen or not. I may not be able to. I'll be careful. I don't want to make a mistake here. Let's see if we can do that. Edit full screen. No, we can't do that. Okay, so turns out we couldn't do that. Well, right up at the top, just past the end of the tab right here, is a star called Deneb. These three stars together, Deneb, Vega, and Altair, make up what's called the summer triangle. No matter where you're observing from, even if you're observing in Center City, you can see the summer triangle without too much difficulty. So that's another way you can find your way around the sky. Here's another one. Now, this is going to be a little bit tricky. going to see if I can make this happen. Sure I can. So you'll see I've pulled the sky down so that we're looking more up toward the top of the sky. Let's go right up here to the very top, a little bit to the right of center. We see the back end of the Big Dipper right here, a constellation that almost everyone knows. Here's how we're going to do this. We're going to take the handle of the Big Dipper, and we're going to use that as a curved line or an arc. And we're going to use that curved line to bring us down to the bright red star Arcturus. And then we'll continue on in that curved line down to this star right here called Spica. So we can come along the curved line to Arcturus, continue along that curve down to Spica, and that gets us through this upper central portion of the sky as well. So that's another way we can do this. There's still one other way to find your way through the summer sky, and that's going to be over here to the east a little bit, and we're going to use Cygnus, Aquila, and Sagittarius as our guides. You can't quite see it as well as we might like to, but the background behind these constellations is actually the edge of our galaxy, the edge of our Milky Way. So if you're out someplace this summer on vacation where the skies are clear and dark, you'll be able to see a lot of stars, but you'll be able to see a band of milky light stretched across the sky at 10:30 in the evening that stretches from the northeast down to the southeast. And that's the edge of our galaxy, the Milky Way. Now, as you stand looking at the Milky Way, if you just point your arms out to the side, you're now looking toward the rotational axis of our galaxy. You're looking at the North Celestial Pole, you're looking at the South Celestial Pole, or I should say, the North Galactic Pole and the South Galactic Pole. So now you can begin to imagine what the arms of the spiral galaxy are shaped like, what the galaxy itself is shaped like. And if you had a spacecraft and could do it, you could head towards Sagittarius and be on your way toward the center of our galaxy. That's the direction you want to head to get to the center of our galaxy, is out through Sagittarius. Of course, the bright constellations down along the lower portion of the sky, Sagittarius and Scorpius, are two of the brightest constellations you'll see all year. They're down low, close to the southern horizon, and this is a good time of year to get out and look for them because they skirt right across the bottom, and they don't spend as much time in the sky as the constellations that are higher. So these are all ways in which you can find your way around the sky. This particular app that I'm using, stellarium-web.org, works really well. It's really easy to use. I encourage you to use it to find your way along. Now, we can connect these stars through to our understanding about the seasons very easily. These are the summer constellations. And what I'm going to do is I'm going to slide us forward hour by hour. So I'm going to use our little time date thing to slide us along. Notice how those constellations in the south come up a bit higher now, and we're at midnight. Now we're at 1:30 in the morning. Look way over to the eastern side. Low in the east, you'll find the planet Saturn is rising over in the east at 1:30. Let's go to 2:30, coming up a bit higher. Notice that Arcturus has now moved off toward the west. Let's go to 3:30. Wow, take a look at this. Way over in the east, Mars has now come up above the eastern horizon. So there are two planets visible in the sky, two of the bright showpiece planets of the sky. There's Saturn and there's Mars. That's great. But it's at 3:30 in the morning. I'm not sure you're going to be up then, but I highly recommend you go out and take a look because it's a cool time to see planets. Over on the eastern horizon at 4:30, we can begin to see that there's some light from the sun beginning to peek up above the horizon. This is now the time called morning twilight. Let's go a little bit further along, but I'm going to do it minute by minute. And the reason why is as the sky brightens in the morning toward 5 o'clock, let's just come down here. There's another planet there. There's Jupiter right there. But the problem is we're getting so close to sunrise, it's hard to see Jupiter in the glare of the rising sun. So if you were out at 4:30 in the morning, check it out. If you had a clear view of the eastern horizon, let's say you're down at the shore for a few days of rest and relaxation at the beach. If you're up at 4:30 in the morning, you might catch 3 planets: Saturn, Mars, and Jupiter. And those are all the planets that are available to be seen through the summer. That's it. There are no planets in the evening sky right now. That won't come about until later this year into the fall. So if you're an early riser, you've got some treats for you. If you're not, you might have to get up early to see those planets. So these are the constellations that are all available. You know about the artwork that goes with them that depict these various stories that have been passed down from Greek and Roman times, from early history down to us. We still use the same stories to go with the constellations, but you don't have to use those. You can make up your own stories. In fact, guess what? You can make up your own constellation shapes. You don't have to use the classic ones. As long as you have a way to find your way around the sky and you're out there enjoying it, that's all you need. I'm going to stop sharing the screen now because we're now coming up to talking a little bit more about a couple of other things that we have left to make sure we cover for you so you're all set for the summer, and then we'll be done. So we talked about why we have seasons. We talked about seasons on other planets. We have talked about how those planets with their tilt, helps to make the seasons happen for them. We talked about aphelion, the Earth being at its greatest distance from the sun right now, and we also included the summer constellations and talked a little bit about seasonality with those summer constellations. We gave you the lowdown on sunrise and sunset for right now, so we covered that. As it turns out, the moon is the major target for us to observe this summer. Binoculars and a small telescope will certainly do it. If you have a larger telescope, that's even better. Right now, the moon is in a waxing gibbous phase. That means it's between first quarter and full moon. Full moon will be coming on Friday. Friday will be full moon, June 21st. The moon right now, or today, rose at 5:31. It's going to set at 2:45 tomorrow morning, but you can get out and look for the full moon over the next several days. Full moon is not the best time to observe with a telescope. It's better to observe either first quarter or last quarter. So if you could do it tonight would be a great night to look at the moon because you want to look at the line that divides the bright portion of the moon from the darker portion of the moon. It's right along that line called the terminator. The terminator. It's the line of sunrise and sunset on the moon. Right along that line, you can actually see relief. And the surface of the moon looks like it has 3 dimensions. You can see height. You can see depth. But when the moon is full, too much bright light doesn't give any shadows, so you can't really see any depth on the surface of the moon. So give that a shot and see how that goes tonight or tomorrow night. Friday, it'll be too close to full moon. It'll be full moon, so don't bother doing it. Really bright? Is it damaging? Eye damaging? Let's say it's very uncomfortable to observe full moon through a telescope. I don't recommend it. Uncomfortable, don't do it. Wait till first quarter to get a good view. Okay, great. So let's see, what else is available for us to see? Well, International Space Station is always a great target to see, and I highly recommend that. We have only overnight passes right now, no evening passes, just early morning passes between midnight and sunrise. But as it turns out, 3 of the brightest passes I've ever heard of will be happening this week coming up, June 22nd on Saturday morning at 4:45 in the morning, right across the top of the sky, one of the brightest passes I've ever heard of. 4 o'clock in the morning on June 25th, another very bright pass. And June 26th, again, early in the morning at 3:15 a.m., all very bright passes. And you can easily look these up and find out all the information you need to know for where to look and when to look, especially if you go to NASA's website and use their tab called Spot the Station. In fact, you can just search Spot the Station in any of your internet search engines, and it will turn up this NASA website that will tell you when and where to look to see International Space Station. It's a really cool site. If you haven't seen it, make sure you see it. If you want to do it early in the morning, this will be a great time to get a really good view, but there are other observing times, just nothing really easy and comfortable. Right now, for the next 2 to 3 weeks, they're all going to be in the pre-dawn sky, after midnight and before sunrise. but still a cool thing to do during the summer. So I highly recommend you do that. Okay, I think we've covered just about everything here. And the only other things I wanted to make sure that you are aware of is we're going to do another Night Skies program coming up on September 12th. You should save the date actually, because that might just be an actual live Sky Tonight program. I'm sorry, Night Skies program at the Franklin Institute. So we're going to invite our friends to come down, all of you that have been with us for a while. We'll invite you to come down and enjoy an evening at the Franklin Institute where we can do night sky stuff right there. We'll have the observatory open, we'll have the planetarium open, and you can come down and join us then. So just save that date and come to the Franklin Institute's website next month, following month, just to check up on that and see how the plans are coming for that. And also, I'll remind you of the Franklin Institute's second Thursday night events. We have two of them coming up soon, July 11th and August 8th. These are great programs at the Franklin Institute where the museum is open in the evening. And I have to tell you, it's like a really great science party. So you've got to come check that out. If you haven't been to the Franklin Institute for a while, or you'd like to see a different side of the Franklin Institute, these second Thursdays are great programs for really getting to enjoy the Franklin Institute in a different way. So I highly recommend those. Okay, folks, we have covered an awful lot here this evening. And hopefully this will be enough to get you started in observing the sky this summer. You have access to a star map, the Stellarium Web online star map that works really well. You know how to find out information about seeing International Space Station. I'm sure you understand to the nth degree now how seasons work here on our planet and on other planets. And hopefully you enjoyed the music that we started with, the Clair de Lune, as depicted by NASA using the Lunar Reconnaissance Orbiter to give us images. And of course, this great image of Saturn back here. If you have a telescope, you can get a great view of Saturn, but you'll have to be up early in the morning this summer. It's a great time to do it. So I think we've covered everything, folks. I want to thank you very much for joining us. It's been great having you with us. If you have questions, don't forget you can always reach out to us, reach out to me at the Franklin Institute without any problem at all. Oh, Mike, I almost forgot. You had a burning question about whether or not there is a supernova that would be visible to the naked eye this summer. Yeah, let's talk about that for a very quick half second. Many of you have possibly heard that there is some expectation that a supernova might occur this summer. Well, as it turns out, that supernova that people have been talking about is a star called T Corona Borealis. I should really say it properly, T Coronae Borealis. Now, Corona Borealis is a constellation between Hercules and, just let me tell you really quickly, right, between Hercules and, there it is, Boötes, between Hercules and Boötes. It's not a very bright constellation, but one of the stars, Gemma, actually is quite bright, and you can see it without too much difficulty. T Coronae Borealis. Now, that particular star, T Corona, is not a very bright star at all. But astronomers over a number of decades have noticed that it has a particular phenomenon, which is a recurring nova-type behavior. In other words, it flares up to great brightness and then comes back down again. Well, it has been noticed by some astronomers that it seems to be mimicking the same kind of behavior that it demonstrated just before it brightened up to nova-level brightness back in the 1940s. I think it was 1946. So because that behavior is being observed, some people are beginning to suggest that perhaps T Corona Borealis will flare up and be bright enough to be seen as a supernova in the sky. I wouldn't even say it's a supernova, but I'd just call it a nova. It's not going to explode. What it's going to do, though, is it's going to flare up in brightness, and that will make it more easily visible at night. Will it get bright enough to be visible during the day? I don't think so. And do we know when it's going to happen? No, we don't. Speculation has been that would happen this summer. Well, that would be really convenient because it turns out that Corona Borealis is a summer constellation, a late spring and summer constellation. So it'd be really great if it would happen right now. But we have no schedule for this, and it's not obligated to occur when we want it to occur. So it could occur anytime over the next several years. But the behavior that it seems to show right now seems to indicate that something might happen this summer. And that's a very big if, a very big if. I personally am not holding my breath. But if you keep your ear tuned to the Franklin Institute and to our astronomy information, we'll be sure to let you know if it looks like something is going to happen soon that you should look for. So there you go, Mike. I think that takes care of your question, hopefully. And please feel free to send us any other questions. Again, thanks for joining us, folks. It was great having you. I hope you have a really wonderful summer. Check back with us to see about our program coming up on September the 12th. We'd love to have you come visit with us. But until then, get outside and enjoy the night sky. Thanks for joining us. We'll see you again soon. I'm Derrick Pitts, Chief Astronomer at the Franklin Institute Science Museum, advising you to enjoy the summer skies. Go outside and take a look. You'll really enjoy it. Thanks for joining us, folks. We'll see you next time. So long.